Welcome to the peripheral nervous system. So my goal is to break this up into multiple sections. We'll see how far we go. Alright, this is kind of an interesting thing. This is a float tank, or what you'll often hear referred to as a sensory deprivation chamber. And what this is going to do is the top's going to close, the lights are going to go out. The fluid that she is within here is a supersaline fluid, so it's very salty to the point of nucleation. And the essence of this is, if you look, she is really floating, alright, really floating, like not even trying to sink. Basically, you'll float about halfway into this fluid and go no further. So it's almost like laying on a cloud. In other words, you have no tactile stimulation whatsoever. When the top closes and the lights go out, there's no vision. It's completely dark. It's got sound deadening technology, so there are no sounds coming in or out. And the temperature is acclimated to your body temperature. So the idea is, when the top of this thing closes down, you have no perception. Okay, you have no peripheral nervous interactions taking place. There is no sensory input coming in. And when you do this, it's kind of like cutting the brain off from the rest of the world. And as I say here, your brain doesn't like to be alone. People report having really strong waking dreams. It sounds kind of creepy, but imagine, you experience things and it feels and seems completely real, but you're mostly in control of it. Float tank treatments have been diagnosed for people with post-traumatic stress syndrome, with people with extreme depression, and apparently it really helps. Like the medical world allows for this in place of chemical treatments, like medications. It works extremely well. So it's a really neat concept. But that is to say that our survival depends somewhat upon our sensations and perception. So survival depends upon sensation and perception. Sensation is our sensing of changes in the external environment, or internal for that matter. That is the things that we feel or perceive. Rather, things that we feel. Whereas our perception is our interpretation. Okay, our interpretation, our response to those stimuli. And really what we're getting at here is this concept of how the nervous system is broken down. And I believe we've already played this game at length, but I'll play it again just a little bit. We've got the central nervous system and the peripheral nervous system. The central nervous system is broken down into the brain and the spinal cord, whereas the peripheral nervous system is broken down into the sensory divisions and the motor divisions. Now, the sensory divisions and motor divisions are further broken down into somatic sensory and visceral sensory, and then motor to somatic motor and visceral motor. Somatic sensory basically means sensations from the body, things that we can detect. Like today we're going to talk about a few things that we are consciously aware of coming in terms of sensation. Like the special senses is a good point here, whereas visceral sensory information is coming in from your organs. Like, what's your blood chemistry like right now? That's a visceral sensory perception. You're not consciously aware of it. Motor division, somatic motor, the only thing that we can have an output and control is our skeletal muscles, whereas our visceral motor division goes out and controls all of our homeostatic functions, like keeping the heart beating, keeping the intestines mobile, regulating the amount of fluid in the bloodstream by actually activating or deactivating kidney function. That's how all this stuff works. So what we're focusing on right now is the peripheral nervous system. In particular, we're going to be talking about somatic and visceral sensory inputs. Okay, let's go here. Peripheral nervous system. So sensory receptors pick up messages and send afferent messages to a control center, be that the brain or spinal cord or other things within the body that act as control centers. But the idea is that a sensory input carries afferent signals to that control center. And then there is a motor output. Those motor outputs are referred to as efferent messages, and these are going to be taking messages from the brain or spinal cord or other control centers back out to other structures. Okay, sensory is bringing information in, motor is taking information out, and I can guarantee you on your exam I'm going to have a big old block of matching or something along those lines. I always do this, where A is sensory and B is motor, and you just got to go through the list and tell me what's what. All right, it's not complicated, but you'd be amazed at how many people make mistakes. Like, it's very, very important understanding this as a concept. Afferent versus efferent transmission. So sensory receptors, boy, can they be highly varied. You have sensory receptors that are as basic as bare nerve endings. Okay, just a bare nerve ending, and when it gets pressure against it or when chemicals flow to it, it will signal a transmission and travel to the brain as a sensory input. Or alternatively, you can have extraordinarily extraordinarily complicated sensory receptors like those in the eyes. The eyes are hardcore sense organs. Okay, you've got in the eye, you've got multiple different types of muscle. You have nervous tissue. You have connective tissues of various different types. I mean, you name it. It's got it. Okay, the eyes are very complicated, and they are basically a sensory receptor. The eyes have sensory receptors internalized, and they are built into a single unit. Alright, and that's sort of what I'm going through and showing you here. Very simple bare nerve endings to slightly more complicated forms of sensory perception, like a Merkel disc situation here that we talked about in the skin. These are kind of binary. They're either saying yes, there's something happening, or no, there's not. Then we get a little more complicated, like we have Meissner's and Pacinian corpuscles, basically. These can detect variations in stimulus form. So in other words, am I touching the table or am I not touching the table? That's what my Merkel discs tell me. And then I can identify the amount of pressure by using my Meissner's and Pacinian corpuscles. Does that make some level of sense, hopefully? That's sort of how this works, okay? And then they get more and more complicated, all the way up to our special senses. So we have vision, our special senses. Special senses are vision, taste, hearing, and equilibrium. And we need to talk about how we classify all of these. Alright, there are three forms of classification for your sensory receptors. The first that we will talk about is by what we call modality, or the form of stimulus they're capable of detecting. So, there are thermoreceptors. Thermoreceptors obviously detect temperature, thermo for temperature. You have these all over the body. Photoreceptors, these are specially set up to detect light. In you, a human, my kiddos. In you, a human, your photoreceptors are entirely in your eyes. You only have photoreceptors in your eyes. Other animals, that's not quite the case. Cockroaches are kind of famous for having photoreceptors all over their body. And this is gross, but I'll tell you anyway. You can cut the head off of a cockroach and shine a light on the corpse, and the corpse will run into the dark. It's the wildest thing. Feel free to enjoy yourself while in quarantine. Moving on, it's just other animals have photoreceptors in other places, is what I'm trying to get at. Now, where are yours in your eyes, and what are they called? Your photoreceptors are called the rods and cones. Rods give you your nighttime vision, it's kind of black and white, and cones give you your really sharp daytime vision that provides you with color vision. Alright, nociceptors. Nociceptors are how you derive pain. Pain sensations come in from nociceptors. Extreme hot, extreme cold, pressure, you name it. Chemoreceptors help us to detect chemicals in the world around us. Your nose is contains chemoreceptors, can detect chemicals in the air you breathe. Your tongue has taste buds, which allow you to detect chemicals in the foods that you eat. Your body has chemoreceptors all in it, like testing your blood chemistry, for example, to make sure you have everything you need and that you don't have problems. So chemoreceptors. Then, of course, there are mechanoreceptors. Touch, pressure, vibration, stretch. Your ears contain mechanoreceptors that allow you to detect sound waves in motion. I mean, modality, by the type of stimulus. These are good multiple choice questions. Work like a charm. Alright, then we can classify receptors by their origin of stimulation. So exteroceptors detect stimulation from the outside of the body, like I can feel this table, I can see that screen. That is exteroception, from outside, and that's what we're mainly conscious of, is our exteroception. Interoception, or interoceptors, detect internal stimuli. This is normally concerned with homeostatic function, so keeping your blood chemistry the way it's supposed to be, keeping your blood pressure regulated, tissue stretch, temperature, internal is the idea. We're detecting internal things. Normally not directly aware. This is interoceptors primarily report to the autonomic nervous system, so that's the homeostatic function. And then last but not least here is by proprioceptors. Proprioceptors are in your joints, so in like your tendons and your ligaments and your muscles, and they basically detect stretch and strain to help you to stay upright. Okay, so the reason that you can stand up and not fall down is because you have proprioceptors all over your body telling your cerebellum the body's position in space, and the cerebellum makes minor changes to your body's position to keep you upright and not falling down. Alright, last but not least, here at the very bottom is by distribution. We will primarily focus on receptor placement by distribution. I like general senses and special senses. The general senses are those which are widely distributed across the body. Like I can feel temperature variation from the tips of my toes to the top of my head. I can feel touch from the tip of my toes to the top of my head. And I can feel, as a better example, potentially pain. Pain sensations are body-wide. They are general senses. And that's the one that we're going to focus on because it's probably one that you don't know as much about. And then obviously there are the special senses. Special senses are confined to the head and the face. This would be vision, hearing, equilibrium, taste, and smell. Special senses. Special. Limited to the head. Alright, so let's talk a little bit about pain. And I'm going to do this pretty quick. It's neat stuff. And it shouldn't take us too long. Alright, so somatic pain versus visceral pain. Somatic pain is what we're more conscious of. Soma means of the body. We are conscious of this. Like I can, if I'm poked by something, I can feel it and it hurts. It's easy for me to localize where somatic pain is coming from. If I step on a Lego, I know it's my foot that hurts. Skin, muscles, joints, what have you. Visceral pain is organ pain. It's hard to localize visceral pain. Like the classic example is referred pain from a heart attack. So if somebody's having a heart attack, so their heart is giving off pain signals, saying that it's low in oxygen, and a lot of times people misconstrue that as like a shoulder issue. Oh, my arm hurts. I don't know what's happening. Or my wife and her famous kidney stone. So when she walked in to tell me that she was hurting, she didn't know what was wrong. She walks in to tell me she's hurting. She goes, I don't know what I did, but I think I pulled a muscle in my back. Man, it's hurting real bad. Then later she's like, oh, it hurts really, really bad. I got to go to the hospital. But the idea is she didn't know it was a ureter pain. No, you can't localize that. She just thought it was coming from kind of generally her back area. So visceral pain is hard to localize. But it is present, ever present, and internalized. Now, how do we detect pain stimulation? Using the following chemicals. Histamine, potassium, ATP, bradykinin, and prostaglandin. The idea is, for instance, potassium and ATP, these should be inside of cells. And if they come out of the cell, that means the cell was damaged. So this elicits a pain response. Bradykinins and prostaglandins, these are specific pain-stimulating chemicals. I could take a syringe full of bradykinin, pop it into you, and boy, you'd hurt real bad. Like it would be a terrible, terrible sensation. These chemicals trigger nociceptors. They trigger pain receptors. Histamine is a good example of this. So the idea is you damage tissues, they release histamine, and this promotes a inflammation response, but it also stimulates a pain signal so that the brain knows sort of what's going on. Now, the actual receptors that detect these chemicals are called nociceptors. And nociceptors have two very highly specialized neurotransmitters called substance P, that will be substance pain, and glutamate. So what will happen is a nociceptor comes in contact with bradykinin, that stimulates the nociceptor, and it releases either substance P or glutamate to then send a message to the brain that there is a pain signal occurring. And it's kind of neat the way that it sends the signal. So it turns out that there are two signals that travel from a nociceptor, a fast myelinated tract and then a slow non-myelinated tract. The fast myelinated tract goes to your primitive brain, and the idea is the fast signal here going to the midbrain, your primitive brain, causes you to respond to that pain signal in a very visceral way to stop whatever it is from hurting you. Okay? Whereas the slower signal travels up into your cerebral cortex and allows you to sort of better understand what just happened. So imagine you're walking along and a bee stings you on the arm. Well, your first reaction is to swat that thing away and get it off of you. That's that primitive, get it away. And then your secondary signal is, man, that hurts real bad. I'm going to learn from this, and I'm going to pay better attention to my surroundings. Pain signals travel through two distinct paths. Pain tolerance is an interesting concept to discuss. So there's pain tolerance and there's pain threshold, and these are not the same thing. Pain threshold is the point at which we all feel pain. I think I've got a temperature example. Yeah. So around 45 degrees Celsius, we all begin to perceive pain instead of heat, as an example. Yeah, no. The opposite of that. Anyway, you get my point. So if I'm poking you with a needle, you would all have a pain signal. It would go from being a mechanoreceptor, standard pressure signal, to a pain center signal, I should say, at the same pressure point. We all will perceive pain, our pain threshold, we all perceive pain at the same basic point. It's just some of us are capable of tolerating pain more so than others. You can handle it better. Some of you can handle pain better than other people can. You know that. This is a fact. And what's fascinating about this is that some of it is genetically derived. For instance, me and my red hair, I've got a mutated MC1R gene. That's what causes red hair. It's an augmented form of melanin that gives a reddish appearance. That's why the hair is red. Okay, and what this does is it plays some hell with other systems also. Good examples of this are people with red hair are famously intolerant of heat variations. So if I get in the shower after my wife's had a shower, man, and it's set the way she likes to have it, it feels like the water will cleave flesh from bone. Like I can't handle it. I can't handle it. It's too hot. Like I have to turn that thing down. Again, it's a genetic thing. I can't handle that extreme heat. Alternatively, and quite fascinatingly, spicy foods, like the chemical that causes spicy food to be spicy is called capsaicin. And people with a mutated MC1R gene can handle capsaicin far better than most people. And I never really understood this. Like, I remember when my wife and I were just dating, and she would come over to my place and I would cook for her, she would always say, man, I can barely eat this. I'm like, why? She says, too spicy. I was like, too spicy? This is not spicy. Little did I know that I was genetically predisposed to not really feeling the spice from spicy food. So these are things that we have to keep in mind in terms of medicine. Okay, we learn a lot about this, and it helps us to treat people better as time progresses. Alright, let's see. Phantom limbs and chronic pain. Yeah, that's good. Oh, well, let's talk about this. So, this is one of my favorite scenes from one of my favorite movies back in the day. If you have never seen the movie Major Payne with Damon Wayans, I think it was his one of his greatest performances. In this, there's an injured person, and the Major goes down and he says, hey, do you want me to give you something to take your mind off that pain? The guy goes, yes, Major, please. So he says, give me your hand. And he breaks his finger. And the guy goes, my finger! The Major says, well, that works every time. So the question becomes, are there ways that we can augment pain signals? And the answer there is, yes, we can. These are called analgesics, mechanisms of augmenting pain relief. And the way that this goes is pretty fascinating. It's referred to commonly as spinal gating, or the capacity to overwhelm neurons as they enter into the spinal cord and kind of close the gate, if you will. And you can see kids do this all the time without any training. Watch a 3-year-old running around, and they slip and they fall and they bump their knee. Do they just sit there and stare at it and cry? No, they don't. They grab it and they squeeze and they rub, because when you're grabbing a hold of the area of the damage and you're squeezing it, you know, doing the thing you do when you're hurt, what this does is it overwhelms all the touch receptors around the area of damage. So instead of getting a really sharp, dagger-like pain feeling from your nociceptors, it overwhelms all the neurons around the spinal cord in that area, and it gives you just more of like a dull ache. I remember getting bitten by this evil bug, man, called a Corsair assassin beetle. Got me right there on the finger. And I sat there and I held that thing for probably 3 hours because it hurt so bad. But if I let go and just let it pulse, it felt like the finger is about to fall off. But if you hold on to it, it just kind of aches. That's because you're overwhelming those neurons. You're putting them, throwing a lot of them into a hyperpolarization state. They become overstimulated, and they don't send the signal in the same fashion as they would otherwise. And here's another very important point to be made. I trust that we have all heard a story of someone being in like a bad car wreck or something like that, and they get up and they drag other people to safety only to realize they have like a broken rib and a broken arm and all this terrible damage. They don't even notice it. That's because endorphins and enkephalins, specifically for our purposes endorphins, are what we refer to as neuromodulators, and they block pain signals, all right? They block pain signals. They decrease the effect of your nociceptors. When you have endorphins flowing through your bloodstream, like this boxer here, he's clearly got some damage. When you have endorphins flowing through your bloodstream, It decreases the way in which you feel pain, and that's a really important point to be made. Opiate-based drugs mimic this effect. This is why we give people morphine in the hospital to decrease the amount of pain that they feel. It mimics the effects of these endorphins, kind of brings you up, makes you feel good, and decreases the amount of pain that you physically feel. Yeah, it's perfect. And then, of course, there's congenital analgesia, which I'm not going to go into a whole bunch of detail on. The idea is that there is a medical condition where people can be born without the capacity to sense pain. And this is obviously very bad. Like, pain is a message. Pain is a teacher. Pain tells you when you're doing something bad. And if you don't have the capacity to feel pain, well, that is just terrifying. So I would invite you to go and look up this and watch some videos. It's pretty fascinating. Not anything I'm going to put on your test, but I think it's fascinating, and you might too. Alright, so what that does is it brings us to our special senses, and that is a long conversation to have, so we're going to stop here, and you can expect another video on special senses coming up pretty soon. Thanks.